In this video, we're going to learn more about limits and how in particular they relate to the definition of being a continuous function. Now, before you've always learned that continuous functions are functions which can be drawn without lifting your pencil off the paper. And that is still true, but that's not a very mathematically precise definition. We're going to get a slightly more precise definition now by using limits to describe what it means to be continuous. So here's our definition. A function, f of x, is continuous at the point x equals a if the limit as x approaches a of f of x is equal to f of a. So what this is saying is a function is continuous at a point if the limit as we approach that point is equal to the actual function value. So let's start by talking about some different functions and whether they're continuous or not. So first example. Let's just find where the function, well, where is this function discontinuous? F of x is x squared minus x minus 2 divided by x minus 2. Where is this function discontinuous? Well, a function is discontinuous where it's not continuous. On this particular function, the only value that causes problems for us is x equals 2. That's where we have something that's undefined. All other values, it's continuous for. Now, I didn't explicitly use my definition of being continuous at a point by just taking limits and seeing if it equals the function value. But it is true, because let's just take a look at the limit as x approaches a of this function. If a happens to be not equal to 2, then I would be able to plug it in to evaluate my limit, and that is equal to f of a. But if a happened to equal 2, we have some issues because I would be dividing by 0 and we'd have problems. Our function's not even defined at 2, so there's no way for it to be continuous at 2. Let's do another example. Is the function g of x equals 1 over x squared if x is not 0, or 1 if x equals 0, is this function continuous at 0? Well, in order for the function to be continuous at 0, we would need the limit as x approaches 0 to equal f of 0. In order for that to be true, 3 things have to actually be true. Your function has to be defined at 0, the limit has to exist at 0, and that limit has to equal the function value. So first, let's check, is g of 0 defined? And it is. If I look at the definition of my function, I see g of 0 equals 1. So it is defined. Now let's find out if our limit exists. The limit as x approaches 0 of g is equal to the limit as x approaches 0 of 1 over x squared. And now what happens as our x approaches 0 in this case? Well, Regardless of whether we're plugging in values to the right of 0 or the left of 0, that x squared is positive. So we get 1 divided by a super tiny positive, and we get infinity. Now, is that limit equal to the actual function value? No, it's not. So we are not continuous at x equals 0. Even though my function was defined there, the limit does not equal that function value. In fact, our limit doesn't even exist as a finite number. Let's do another example. Is h of t, which is equal to t squared minus p minus 2 over t minus 2, if t is not 2, and 1 if t is 2, is this function continuous at t equals 2? Well, let's check. Does h of 2 exist? H of 2 equals 1, so it is defined. Now, in order to see if this function is continuous at t equals 2, we have to check the limit as t approaches 2. If when I check that limit, I get the same answer as I got here, 1, then it's continuous. If I get anything else, it's not. So let's check the limit as t approaches 2 of t squared minus t minus 2 over t minus 2. Well, if I plug that 2 in, the denominator is 0, and the numerator is also 0. 0 over 0, that means we need to do some algebra. And probably the best thing to use is factoring. So go ahead and factor the numerator. And I will get a t minus 2 and a t plus 1 as the factored form. So now that it's factored, you can see that the t minus 2's get to cancel. You can cancel those common factors. So now my limit is just the limit as t approaches 2 of t plus 1. When I plug that 2 in, I get 2 plus 1, which is 3. So is my function continuous at t equals 2? No, it's not. Because when I took the limit as t approaches 2, I got 3, but my actual function value is 1. They don't agree, so it's not continuous. Now, before I erase this example, could we redefine this function a different way to make it so it is continuous at t equals 2? Yeah, absolutely. If we were told to try to fix this function so that it actually is continuous, well, what we would need is instead of this to be a 1, we would need this to be 3. Because we already know the limit is equal to 3, and then that would make my function value equal to 3 as well. So if this problem were written with a 3 there instead of a 1, it would be continuous at t equals 2. All right, time for a definition. A function is continuous from the right at x equals a if the limit as x approaches a from the right side of f of x is equal to f of a. And then similarly, it is continuous from the left. At x equals a. If the limit as we approach a from the left side is equal to the function value at a. So in order for a function to be continuous at a point, it needs to be continuous from the right and continuous from the left at that point. If it is continuous from the right and the left, then both of the limits from the right and the left are equal to each other, which means the actual limit exists and would also be equal to f of a. So all we've talked about so far is a function being continuous at a point. That's not talking about a function being continuous on an interval. So that is our next definition. A function is continuous on an interval if it is continuous at every point in the interval. So our definition of being continuous at a point, you would need to make sure that held for every single point in the interval. Of course, you're not literally going to check every single point because there's infinitely many points in your intervals, but you would be able to check it generically to see if this works. Now, let me give us a theorem about some continuous functions. If f and g are continuous at a and c is a constant, then f plus g, f minus g, c times f, and f times g are continuous at a. And if g of a is not 0, then f over g is also continuous at a. So what this is saying is if you have continuous functions and they're continuous at the same point, you can add them, subtract them, multiply them by a constant, and even divide them, provided the denominator is not 0, and you'll still have a continuous function. In particular, any polynomial is continuous for all real numbers. Polynomials are going to become one of your favorite types of functions if they're not already there. Polynomials are very well behaved. They end up being very nice to work with calculus. A lot of the things that we are going to learn in calculus are very straightforward when working with a polynomial. Polynomials are continuous everywhere, and because of that, in the previous theorem, our rational functions, which remember are polynomials divided by polynomials, are continuous wherever they are defined. So if you have a polynomial, it's continuous everywhere. If you have a ratio of polynomials, it's continuous everywhere except for places that make the denominator equal to 0. Another type of function that comes up a lot in calculus are trig functions. And our trig functions are continuous at every point in their domain. So this is saying, as long as the trig function is defined at the point, it's continuous at that point. So all we have left for this video is a very, very important theorem that involves using continuous functions. So let's learn this very important intermediate value theorem and do an example where we apply it. And then that will be it for this video on our continuous function. The intermediate value theorem says to suppose that f is continuous on a closed interval a to b. And we're going to let n be any number between f of a and f of b. And this is where f of a and f of b are different. Then there exists a value c in the open interval a, b, so that's a c in between a and b, such that f of c is equal to n. So what this is saying is if you have a continuous function on a closed interval, then for any value in between the function values of the endpoints, you'll be able to find an input in between a and b that gives you the result you're looking for. That sounded kind of confusing, but let me draw a picture and that will make it much more clear. So for our picture, this is what the intermediate value theorem is saying. Here's A, here's B. We'll just say f of A is here, f of B is here. And in between there, we just have a nice continuous function. We'll just say that's our continuous function, f of x. The intermediate value theorem says that you can pick any number between f of a and f of b. So we'll just say, let's pick this number right here. We'll call this one n. And then there will be some value c in between a and b that satisfies f of c equals n. Let's see if this is true. If I move over, I see there's a point on my graph right there where the y value is n. And if I follow that down, this would be my c value. F of this c is equal to n. And that c fell in between a and b, just like the theorem said it should. Let me do one more on here just to emphasize the point, because the theorem says any n, this will be true. So let's pick this one. If this were n, again, follow it over. Oh, there's a value of my function. I could use this c. And that c is also in between a and b. And notice that there can be more than one value that satisfies it. I have another one right here that would work for that f of c equals n. It's okay to have more than one. The theorem just says there will be one that works. So let's do an example where we're going to apply this intermediate value theorem. This is one of the most common ways this theorem is used. This example says, show that there is a root of the equation 4x to the third minus 6x squared plus 3x minus 2 equals 0 between 1 and 2. So this doesn't even tell us to use the intermediate value theorem, which is why it might be a little bit tricky. But what they're asking us to do is find a number in between 1 and 2 that when I plug it into this particular equation, I'm going to get 0. But it's a little bit less specific than that. It doesn't say actually find this value. It just tells you to show that it exists. So this makes our lives much, much easier. To show that it exists, well, we're going to want to use this intermediate value theorem. Let's first just figure out what f of 1 and f of 2 are. F of 1 is equal to 4 times 1 to the third minus 6 times 1 squared plus 3 times 1 minus 2, and that just happens to be equal to negative 1. F of 2 is 4 times 2 to the third minus 6 times 2 squared plus 3 times 2 minus 2, and this equals 12. So my intermediate value theorem tells us that for any n that is in between my f of 1 and my f of 2, there is going to exist some c where our c happens to be between 1 and 2, such that f of c equals n. Well, okay, but what were we trying to show in this problem? We're trying to show that there's a root. That means we want this n to be equal to 0. Notice n equals 0 does fall in between negative 1 and 12. We have a positive number and we have a negative number, and 0 falls in between that. So if we choose n equals 0, this means by that theorem, there is a c in between 1 and 2, such that my equation has that root. So such that my f of c equals 0. This c is the root. Now, notice we still don't know what that c is, but that's okay. The problem did not ask us to find what the c is. They just asked us to show that it exists, and we did. So using the intermediate value theorem, primarily it's used to show that a root actually exists for a particular situation. And you do that by just plugging in the endpoints and showing that one side or one endpoint gives you a positive number, the other endpoint gives you a negative number, and that means there must be a root somewhere in between as long as you have a continuous function. So that's all I have for you for today, and pretty soon we're going to be moving on to doing more with our limits, to moving on to something called a derivative in calculus. And derivatives are one of the big topics in Calc 1, so we're coming up to that pretty soon, just a couple videos away. If you have any questions, feel free to drop them below. If you're in my class currently, you can also email me your questions or ask in office hours, and I will see you for the next video.